Alright, let's get started. The paper I'd like to talk about today is called Neural Ordinary Differential Equations. It was published in NeurIPS 2018 and won the Best Paper Award. And as of now, it has been cited more than 7,500 times, which shows just how influential it has been. So here's what we'll cover today. First, I will give a quick introduction to the main idea behind neural differential equations. Then I will go over some basic math concepts about differential equations and numerical solvers, just enough to help us understand how these models work. After that, we will define the three main frameworks: NeuralODES, NeuralCDEs, and NeuralSDs. Next, I will explain why we care about neural differential equations and what makes them interesting. And finally, we will wrap up by looking at their theoretical guarantees, applications, and training method. So let's talk about the main concept of neural ordinary differential equations. In traditional deep learning, we stack a fixed number of layers to transform inputs into outputs. But NeuralODES work differently. They treat this transformation as a continuous process. Instead of defining discrete layers, they use a neural network to model how the hidden state changed and then solve an ODE with a black box solver to get the output. Before dive into neural differential equations, let's quickly talk about some mathematical background. So what exactly is differential equation? Simply, it's an equation that relates a function to its derivatives. In other words, it describes how something changes over time. Differential equations are fundamental for modeling systems in many fields. Let's look at an example. The SIR model, which describes how an infectious disease spreads. By solving a SIR model, we can predict how the numbers of susceptible infected and recovered individuals change over time. Another simple example is the predator-prey model, which describes the dynamics of two species interacting within a biological system. However, unlike the previous examples, most differential equations can't be solved analytically. So we use numerical solvers to approximate their solutions. There are many solvers to choose from depending on the accuracy we need, and the simplest one is Euler's method. In Euler's method, we start from an initial point and estimate the next value by taking a small step along the slope given by the derivative. By repeating this process, we approximate the entire solution curve. Of course, we can also choose more advanced methods to obtain better and more accurate solutions. So what are neural ordinary differential equations? In NeuralODES, we represent the vector field using a neural network. To get our model's output, we start from the initial value y0 and solve this differential equation by integrating the neural vector field over time until the final time step. If we go one step further, we can think about integrating not just over time, but over the data itself. In a standard ODE, once we set the initial value, the entire solution curve is fully determined. But when we have ordered the input data, we can continuously incorporate incoming information into the dynamics. This gives us the controlled differential equation. Instead of integrating over time alone, we integrate over the input data. Here y is the hidden state of the system, and it is updated continuously as new observations X arrive. Intuitively, you can think of this as being very similar to an RNN, where the hidden state adapts to incoming data. Unlike a regular ODE, where the entire trajectory depends only on the initial value, a CD adapts dynamically as the data evolves. And finally, just like NeuralODES, we parameterize vector fields with a neural network, and that gives us NeuralCDEs. So to recap, NeuralCDEs are NeuralODEs whose dynamics are driven by the data stream. Finally, we take one more step. This time, the driving force is not the observations but random noise. In the equation, the first term is the usual drift, and the second term integrates over Brownian motion. If there's no noise, so when ignore the second term, then we recover the regular ODE. But when we add the random diffusion term, we get a stochastic differential equation. You can think of this as a generalized framework. There is some hierarchy from ODE to CD to SDE. In experiments, you will see that SDEs can approximate both the deterministic and random dynamics, but ODEs cannot capture random behaviors. And finally, just like neural ODEs and neural CDs, we parameterize the vector field with a neural network, and that gives us neural SDEs. So to recap, neural SDEs are neural ODEs with randomness added. They model stochastic dynamics where random noise is continuously injected into the system over time. Now we have defined neural ODEs, CDs, and SDEs, and we have built some intuition behind these equations. But the real question is, why should we care about neural differential equations? What makes them interesting? Indeed, many of the most effective and popular deep learning architectures resemble differential equations. Let's recall the formulation of a residual network, where f theta represents the residual block. Now think about the neural ODE formulation. If we discretize neural ODE using the Euler's method, we can recover the residual block formulation exactly. This observation shows that neural ODEs are the continuous time limit of residual networks. And once we see this connection, it naturally prompts us to explore other links between differential equations and modern neural network architectures. But before we move on to the other connections, let's think about this. What are the differences between ResNet and neural ODEs? You can find the answer in the appendix. So let's move on to the next connection. It turns out that neural-controlled differential equations are the continuous time limit of recurrent neural networks. In other words, just as neural ODEs generalize ResNet to continuous depth, neural CDs generalize RNNs to continuous time, continuously updating the hidden state as new data arrives. Even architectures like GRUs and LSTMs can be seen as applying update rules that resemble discretized differential equations. The connection to RNNs is intuitive. Just like controlled differential equations, RNNs compute a function of their time-varying inputs to update the hidden state at each step. As with other cases, a numerically discretized neural stochastic differential equation also has a natural correspondence in the deep learning literature. Similar to neural CDs, the closest analogy is an RNN. But here the input is random noise and the output is a generated sample. Now we know that with neural differential equations, we can build continuous depth deep learning architectures. But you might wonder, do solutions to these equations actually exist? And from a practical standpoint, what kinds of functions can these models approximate? Without loss of generality, neural networks are usually built as compositions of Lipschitz functions. Because of this, for most architectures, the existence and uniqueness of solutions are guaranteed. Under mild smoothness assumptions, neural ODEs are well defined, and Picard's theorem provides the theoretical guarantee that a unique solution exists. Similar results also hold for neural CDs and SDs, so these models are mathematically well founded. You can find formal theorems and proofs in the references listed below. What kinds of functions can neural ODEs approximate? Generally speaking, under mild conditions, augmented neural ODEs can approximate any continuous mapping. Interestingly, the vector field F itself does not need to be a universal approximator. Similar approximation results also hold for neural CDs and neural SDs. You can find formal theorems and proofs in the references listed below. Now we know that we can actually solve neural differential equations and that they can in principle model any continuous mapping. Of course, these theoretical guarantees don't automatically ensure good empirical performance, but they do give us confidence that such modeling is possible in principle. So let's move on to the practical side. What kinds of problems can neural differential equations actually tackle? First, neural differential equations can be used for generative modeling. A notable example is continuous normalizing flows. As you know, generative modeling aims to run the target data distribution when we only have samples from it. The common approach is to start from a simple base distribution and run a mapping that transforms it into the target distribution. It turns out that some of the most effective mappings naturally arise from differential equations. For example, continuous normalizing flows transform a normal distribution into the target distribution. Normalizing flows transform a simple distribution into a complex one using a change of variables formula. However, standard flows require computing the determinant of Jacobian, which is cubic in cost and limits model expressiveness. Continuous normalizing flows solve this problem by replacing discrete layers with a continuous transformation. In CNF, the change in log density is given by the instantaneous change of variables formula, which only needs a trace instead of a full determinants. This makes CNFs much more efficient, enabling expressive flow models with many hidden units at a cost linear in the number of units. Here's a simple experiment on learning a distribution. We feed a continuous normalizing flow to map a standard normal distribution into a target distribution. The figures show how the distribution evolves as the CNF integrates from the initial to the terminal time. We can see that CNFs are capable of learning complex multimodal two-dimensional distributions. Overall, CNFs provide a highly flexible framework for modeling probability distributions, with many applications such as image generation and point cloud modeling. Now let's see how CNFs can be used to model real continuous time dynamics. This example is from a model called TrajectoryNet. In many cases, like in biology, we only have data collected at separate time points, kind of like snapshots, not fully continuous trajectories. Usual methods can connect these snapshots, but they can't describe how things move smoothly over time. TrajectoryNet fixes this by using CNFs together with dynamic optimal transport so it can model how points continuously move from one distribution to another. Similarly, in score-based diffusion models, the mapping is defined by a neural SDE, where the dynamics are driven by Brownian motion. It allows us to sample from complex high-dimensional distributions such as images. Another example is molecular conformation generation, predicting stable 3D shapes of molecules from their 2D graphs. The model called ConvGF runs the gradient field for the force that pushes atoms towards stable positions. Then, using Langevin dynamics, it can generate realistic and stable molecular shapes directly. This is a nice example showing how neural SDEs can model random physical processes, like how molecules naturally move and settle. The second application is generative modeling as well, but this time we focus on time-varying data rather than static distributions. Here we aim to model distributions over time series. A key example is a latent ODE. It represents each time series as a latent trajectory determined by an initial state and latent dynamics. The model is trained as a Bayesian autoencoder. The encoder processes the observed sequence and produces an approximate posterior for the initial state. Then, given this initial state and the observation times, an ODE solver computes the latent states at each time point and can even predict values at arbitrary times on a continuous timeline. Here's a simple example of fitting a latent ODE to a dataset of decaying oscillators. The figure shows samples generated from the trained model which perfectly match the true dynamics. The training data are irregularly sampled. Each sequence has observations at different time points. Yet the latent ODE can generate smooth trajectories over the entire continuous time interval, producing samples at any time. Moreover, it generalizes well beyond the training range, demonstrating a strong extrapolation ability. The next example is SDE GANs. Previously, we saw that latent ODEs are trained using the Bayesian autoencoder framework. This time, we train a neural SDE as a generative adversarial network. Neural SDEs are continuous time generative models for time series, and they can be fitted using Wasserstein GANs. Here's how it works. The generator is NeuralST that takes Brownian motion as input and produces time-evolving sample path using a numerical solver. The discriminator is a NeuralCD, which evaluates these generated paths against the real data. By coupling NeuralST and NeuralCD as a generator-discriminator pair, we can train continuous time GANs that model distributions over entire path space. Here's a summary of equations for an ST GAN. Here's a simple experiment where we train a ST GAN to match the distribution of samples from the Ullstein-Uhlenbach process. This process has both non-trivial drift and diffusion components, and as you can see, the ST GAN does a great job recovering the true distribution. This is an experimental result from ST GAN on real-world dataset. I'm showing experimental results from ST GAN rather than the ones from the original paper because the experiments in the original work were mostly toy examples or simple tasks like image classification, which is just other deep learning models already perform very well, so there's a little to be gained from them. And also it has been almost 7 years since the original paper was published, and during that time there have been many advances. So today I will focus on these more recent innovations and applications. So here's an experiment on the largest stock price dataset with about 13.6 million data points, comparing three models: NeuralST, continuous time flow process, and latent ODE, trained as GANs, normalizing flows, and variation autoencoders. Performance is evaluated using three metrics: classification, prediction, and maximum mean discrepancy. As shown in Table 1, NeuralSTs outperform both other models across all metrics. The latent ODE fails completely mainly because it can't capture the stochastic nature of stock price dynamics, showing the clear advantage of NeuralSTs for modeling real-world stochastic systems. The final application is challenging time series problems. In the real world, time series data is often messy and irregular. Different channels may be recorded at different frequencies, missing data is common, and sequences can have variable length. Neural differential equations provide a powerful framework here. By treating discrete observations in a continuous time regime, we can naturally handle irregularly sampled data and process it on the same footing as regularly sampled data. This makes them especially useful for fields like healthcare and anywhere messy time series data is common. Here's a visualization of fitting a latent SE to the samples. This process can be viewed as a form of Bayesian learning where the model infers uncertainty over continuous dynamics. And here is some visualization of fitting latent SE to Lorentz attractor. In all experiments so far, the data are irregularly sampled with missing observations. Each point is observed only about 70% of the time. But since the model works in continuous time, this irregularity doesn't need any special handling. The model's output also evolves continuously, so we can evaluate or visualize it at any time point we want. Neural differential equations can also tackle many other challenging time series problems. For example, dealing with discontinuities or detecting change points in systems where the dynamics switch over time. Here's an example of Lotka-Volterra hybrid trajectories with varying numbers of change points. The latent segmented ODE model is able to detect those change points accurately and recover the true underlying dynamics. Here is some visualization of two bouncing balls with collisions. The neural event ODE model runs to capture realistic motion. It predicts smooth floating behavior and straight trajectories between collisions, closely matching real dynamics. Now we know that neural differential equations can model continuous dynamics, from generative modeling to time series forecasting and beyond. But here comes the key question: how do we actually train these models? There are two options for backpropagation through neural differential equations. The first option is simply backpropagate directly through the internal operations of the solver. A differential equation solver internally performs basic operations which are differentiable. The advantages are accuracy and speed. Because we directly use the same computations from forward propagation and the full computation graph is known, we can rely on automatic differentiation. However, it is memory inefficient because we must store every intermediate operation of the solver, which is sometimes infeasible for deep simulations. The second option is called the adjoint method. Instead of storing everything from the forward path, this method works by setting up a new differential equation that runs backwards in time. We then solve this adjoint equation numerically to compute the gradients. The advantage is memory efficiency, since we don't need to store the entire forward computation. But there are trade-offs. First, it is more computationally expensive because we have to recalculate y during the backward path. Second, we introduce truncation error since the forward and backward solutions for y may not perfectly match. And finally, the adjoint equation itself must be solved numerically, which brings in additional numerical error. Let's take a closer look at what the adjoint method actually does. When we train a neural ODE, we need the gradients of the loss with respect to the model parameters. Now, instead of storing every intermediate state during the forward path, the adjoint sensitivity method computes these gradients by solving an augmented ODE backwards in time. Here's the idea. We define an adjoint variable. This measures how the loss changes with respect to the hidden state. The adjoint itself follows its own ODE, which we integrate backward from the final time all the way back to the initial time. While integrating backwards, we recompute the trajectory y and calculate two things at the same time. The gradient with respect to hidden state and the gradient with respect to the parameters theta. All of these can be handled in a single call to the ODE solver. Okay, let's wrap up. Neural differential equations parameterize the vector field of the differential equation with neural networks, elegantly combining two dominant paradigms, neural networks and differential equations. An important point to note is that, in many cases, we can't really explain why a deep learning model works well or fails. We just rely on empirical results. Differential equations, however, provide a theoretical framework to understand and analyze these behaviors. Since their introduction, neural ODEs have inspired many extensions, such as neural CDs and neural SDs, and enabled a wide range of applications: continuous time dynamics modeling, smooth density estimation, generative modeling, and handling irregular or discontinuous time series problems. Neural differential equations remain a powerful and evolving framework, with vast potential still being actively explored.